we're going to talk a little bit about, okay, so we're recording. We're talking about section 2.6, numerical method, and what they mean here is Euler's method. So, of course, you've had some experience now solving some differential equations and getting explicit solutions for the differential equations. But the fact is there are many differential equations where you cannot get an explicit solution. Even though we have all these methods, like a nonlinear differential equation that's a nonlinear differential equation, oftentimes it's very difficult to get explicit solutions for those. But nevertheless, we want to be able to estimate what the solution is for certain values of x or certain values of t, and we need a way to do that. And so Euler's method is a way to do that. Invented by Leonhard Euler many years ago. So what you do is you assume you have the initial value problem, dy dx equals some function of x and y, okay, where you have an initial value there. And what we want to do here is, well, here they give they actually mentioned right here, this is a like if you have y prime equals 0.1 times the square root of y plus 0.4 times x squared, they say that this nonlinear differential equation cannot be solved directly by any of the methods that you've learned so far. Nevertheless, we can still find approximate values. We can still find approximate values. Hold on, let me get that showing there. Yeah. So now one moment here. I want to do this smoothly. So I'm bringing up my textbook copy here. So I want to really just go to this figure here, this figure. So in this figure, they show that, so like for this nonlinear differential equation, y prime equals 0.1 times root y plus 0.4x squared, where y of 2 equals 4. They've drawn the direction field, which you can, since you have the differential equation, you can get the direction field. That's what they're showing here in figure 2.6.1. And hold on here. So the solution, of course, passes through the point 0.24. Okay, and there's your solution curve. And they're magnifying the solution about the 0.24. And you can see that there is that about that curve right near that coordinate 2,4, the curve basically looks linear. Okay, and the thing is, if we have a derivative and we have a point, we can get the equation of a line. So how do we use this? How do we take advantage of this? We make use of what's called linearization, and I think it's best just to look at a picture here. So look here in figure 2.6.2. Here they have a solution curve, and they have a point x naught, x sub 0, y sub 0 on the solution curve. And let's say that they want to estimate the value of the solution when you're at the value x1, where x1 is a step size h away from x sub 0. So you start off with initial condition x sub 0 comma y sub 0. That's a point on the solution curve. But you want to estimate what the solution is at x1. x1 is a distance step size h away from x sub 0. So what you can do is, because you know a point on your solution curve, x sub 0 comma y sub 0, and you would know the derivative of at that point, because you have a differential equation, because you have a point and you then have a slope, you're able to graph you're able to find out the equation of the line that's tangent to the solution curve at the point x sub 0, y sub 0. And you see the point x sub 1, y sub 1, okay, that y sub 1 is an approximation to the true value y of x sub 1. And so there's an error in your solution. I mean, there's an error in the approximation. Okay, that's what they point out here in figure 2.6.2. And there's going to be an error anytime you try to approximate a real value with an approximate value. You're going to get an error. But the point is you're able to use this approach by this linearization approach to approximate true solution values with approximate solution values, and that's called linearization. And you've seen that in your Calculus 2 class. Of course, you've seen linearization in Calculus 2. So that's what Euler's method is. And you see, you can keep doing this process. You can once you have your point x sub 1, y sub 1, well, you can go ahead and figure out what the tangent line is there, or I don't want to call it tangent line, but the linearization is there, and then you can step out along the slope field, and you can keep approximating values. And obviously, your approximations, your approximate values to the true solution values will get worse as you move out away from the initial point x sub 0, y sub 0. And I want to get to an example, but I want to get right to an example, but hold on. I want to get to the Euler's formula. Hold on here. Here it is, right here. This is the Euler's method formula. Okay, that's the Euler's method formula. Y sub n plus 1 equals y sub n plus step size h times the value of the derivative at x sub n, y sub n, where x sub n is equal to x sub 0 plus n times h, and n goes 0, 1, 2, and so forth. Okay, that's your Euler's formula. How many recall that from Math 182 or Calculus 2? It's pretty standard that it's covered. Okay, Wajija recalls it, and Matthew vaguely, but okay. So on that note, I want to go just right to a solution that's going to incorporate a lot of things from section 2.6. So let me go ahead here and bring up the example. Okay, this is the example, and I'm going to give you a moment, well, more than a moment, give you a little time to copy this example down, and then we'll work the example out. Okay, so take a little time to copy it down, and I'll be right with you. Okay, all right. So here you have an initial value problem. Here you have an initial value problem. Y prime equals 0.2 times x times y, where when x equals 1, y equals 1. And we're going to use this Euler's method to approximate y of 1.5 with a step size of 0.1. That's part A of the problem. And then in part B of the problem, we're going to approximate y of 1.5 using a smaller step size of 0.05. Okay, smaller step size. And then finally, we want to compute what are called the percentage relative errors of the Euler method approximation of this solution of 1.5 for both of these step sizes. So this is something probably you did not see in calculus 1, calculus 2, these percentage relative errors. Okay, now let me ask you, for this differential equation, do we actually need Euler's method to, we want to find out what the solution is, here. Let me do it right here. We want to find out what the solution is when x equals 1.5. And that's right, Mark. Mark says no, we don't need Euler's method. Why not, Mark? Why not? Okay, good, Zachary. Good, Michael. Very good. You can separate the variables. So technically, we don't need to use Euler's method to find an approximate solution for y of 1.5, because we can get the exact solution. We can solve this explicitly. That's right, Michael. We can get the exact answer. And what I want to do is, for this problem, I want to actually get the exact answer, because we're going to need to use that to help us with part C. So I'm going to, may I move forward here? Does everybody have the example copied down all right? Okay, very good. Thank you. All right, well, let's move forward here. So what I'm showing you here is something you're very familiar with. The differential equation is separable, and we can find an explicit solution. So I separate the variables, I integrate both sides, okay, and I'm just going to let you, I think, let me just let you copy down to here, okay, and I don't think I need to really talk about each step, because you know how to separate variables. That was on the test, right? All right, so let me let you copy a little bit. Let me know if you have any questions. That's right, Wajija. This is without Euler's method. What we're doing is, we haven't even started parts A, B, and C of this that we're supposed to be working on. We haven't even started that yet. We're just going to find the exact solution, again, because we're going to need it for part C. All right, very good question. Here, there was a question. Yes, it's sort of interesting, Matthew. You're right. I mean, we use Euler's method for traditionally. I mean, we use Euler's method for differential equations that we cannot solve explicitly. So for many of your homework problems, for some of your homework problems, you're just going to be using Euler's method straight, just to find an approximate solution. But for this problem, since they want to basically you to be able to discuss what the error is using Euler's method to approximate the solution of x equals 1.5. To do that, to do that, for percentage relative error, we need to compare the approximate solution to the exact solution. And that's why we're getting the exact solution. It's sort of like an experimental thing, you know. And, you know, well, yeah. So that's why we're doing this. Let's see, would we be able to do part C without it? Yeah, so we could not, Matthew, we could not do part C unless we could find the exact true value for the solution. We could not formally, well, I want to be careful, at least for at this level, in the section, the book we're using at this level, the answers, we could not answer part C without getting the exact solution. But if you take a course in numerical analysis, I think it's been so long since I've had that, but I'm pretty confident you could get an estimate of your error. Because like even in calculus 2, you have estimates of errors like due to, you know, midpoint rules and trapezoidal rules and stuff like that. So there has to be one for the Euler's method where you know, can't find like the exact solution. But, you know, we'll just go with this for now. All right, so I get down to here. Good question. I get down to here. I have to exponentiate both sides, and then e to the c to the first power is c to the c sub 2. Are we ready to move to the next page? Okay. Matthew's good. I want to make sure I'm pacing myself well. Andre's good. And Thomas, and all right, very good. So we continue then. We continue. So, okay, thank you, Christopher and Andrea. So the absolute value of y equals c2 times e to the 0.1x squared. And then when I drop the absolute values, y is going to equal plus or minus c2 times e to the 0.1x squared power. Well, plus or minus the c2 then, I'm going to call that the constant c, because I know that's going to be my final constant. And so this is a general solution here. This is the general solution. Okay. And now we put in our initial condition where y of 1 equals 1 to solve for that constant c. So of course, when we have an initial value problem, under normal circumstances, we're going to get a unique solution, one unique solution, and that means we use the initial value to solve for the constant c. And it turns out that c is going to equal to e to the negative 0.1 power. And this means then that the solution to the initial value problem is going to be y equals e to the power negative 0.1 plus 0.1 times x squared. Okay, let me give you a moment to catch up here, and if you have any questions, please ask.
Professor?
Yes, Wajija, yes.
So for the line above the last one, you just plugged in, right? And then you're, okay.
Right here?
At the very bottom.
Oh, at the very bottom, okay.
Okay, you just plug in C to the original.
Well, C was determined to be that. That's exactly right. This C here,
Right.
I plugged it in right here. That's right.
Okay.
That's right. Right there. Okay, very good question. Okay, are there any other good questions? And you're going to have a problem similar to this in your homework. So you should, I would say, redo this again, just so you're kind of used to that, uh, and all right. So may we move on? Are there any questions? Okay, great, great. All right, well, now then, we're going to talk about the Euler's method. So here's the Euler's method right here. And part A says approximate y of 1.5 using a step size of 0.1. So of course, when you apply the Euler's method, you always have to think about, well, how many steps do I need to use? And like this problem, you're starting off at x equals 1. So that's going to be your x sub 0. And with a step size of 0.1, in order to get to 1.5, you have to hop out 5 steps to get to 1.5. So that's why you're going to need to do 5 iterations. And this little picture, I don't know, how many of you find this little diagram kind of helpful to show? Okay, good. And I was debating whether to include it or not, but Ann and Andre like it, and so I feel good. Good. Matthew likes it too. Wonderful. And Thomas, excellent, excellent. Okay, so so normally like the textbook will have a table. This problem corresponds to the second example in your textbook, and they have things in tables. They have like your x values and y values in a table, and that's fine. I like to be, hey, we start here, x sub 0 equals 1, y sub 0 equals 1. X sub 1 is going to be 1.1. We can see it based on the little picture here. But also, here's the formula on how to get your x values. X sub n equals x sub 0 plus n times h. Well, in this case, x sub 1, n is 1. So x sub 1 is 1 plus 1 times 0.1. You can graphically see x sub 1 here. And, hey, it equals 1.1. So that means then that y sub 1 is equal to y sub 0 plus h times the value of the derivative. That's what this, I mean, where the scenario is that dy dx is equal to f of xy, right? So dy dx equals this little function f of xy. And so that's why when at the values x sub 0 equals 1 and y sub 0 equals 1, this here is your value of your derivative, because dy dx equals 0.2 times x times y. And that's how you get 1.02. Are there any questions on this first part? Let's see. Antonio says, why does this equal 0.2?
Yeah, can you explain
I
that
think,
again?
let me see. In the differential equation, let me go. I'll come right back. Hold on. So you see here, Antonio, in the differential equation, y prime equals 0.2 times x times y. Okay, all right, very good, very good. And let me go back here. Okay, so, all right, so first iteration, y1 equals 1.02. Now, when x2 is equal to 1.2, we're going to compute y sub 2. Y sub 2 equals y sub 1 plus h times the value of the derivative at x1, y1. So you see, you're always using, you're getting updated values of your updated approximate values of the solution based on the past values. So you can see you're using y sub 1, that was 1.02 from the previous step. And yeah, and you just, you work it out. How many is this kind of ringing a bell now after seeing this? How many of you is this ringing a bell? Okay, Zachary. Okay, good, Zachary. Yes, Matthew, question?
Where do the, next to the 0.2 in the y1 equals section, where does the, like, what are those, like, after f at, 1, comma 1, where does, like, where does the stuff next, the two ones next to 0.2 come from?
Oh, okay, all right. So, good question. dy dx was equal to 0.2 times x times y. So this on the right.
Oh, okay, you literally just, okay, sorry.
All right, no problem. Good question. Okay, so only 3 more iterations to go. All right. May we move to the, okay, all right.
I see that for for y2, you have multiple decimal places. Is there like a range you want us to go to, or?
Well, that's a good question, Christopher. What I'm doing in this problem is I'm going to go out to the 100 millionths place. Okay, that's eight decimals past the decimal point, 8 numbers past the decimal point. And the reason I'm doing that is I know WebAssign is very picky about answers, and so I don't want to, I want to make sure I'm using enough accuracy in my answers. So I'm going out 8 decimal points. Of course, here I've only gone out 1.04244. That's what, tenths, hundredths, thousandths, 10,000. That's out to the 100,000ths place, but you'll see on the next one. Okay, all right. All right, let's go to the next page then, if we're good. Here's one more iteration. And now, so y sub 3 equals 1.06745856. and that's rounded to the 100 millionth decimal place. So basically eight decimal places. And you can compare that with table 2.6.3 from the second example. They don't go out that many decimal places, but I'm just trying to, I'm thinking about you doing WebAssign, and it's possible you could do a process right, but WebAssign doesn't take the answer because you're not carrying enough digits, and I don't want that to happen. I don't want that kind of thing to happen. So I'm being safe and going out 8 decimal places. So, but what I'm going to do for the 4th and 5th iteration, I'm going to actually use a MATLAB program. I'm going to use a MATLAB program. Okay, and I'm going to show you that MATLAB program. I think what I'd like to do is I'll show you the MATLAB program that gets us here. So y sub 4 is 1.09521248, and then y sub 5, which is the value we're looking for, is 1.125878843. So with a step size of a tenth, h equals a tenth, Euler's method estimates that y of 1.5 is equal to 1.125878843. Okay, and I'll show you the MATLAB program in a moment. But I make a note here that the exact value of our solution when x equals 1.5, I just put it in the formula, 1.5 in the explicit solution, and we're going to get 1.1331485. So in that case, we get agreement to the tenths place between our approximation and our exact answer. How many are happy with approximating the exact answer to within the tenths place? How many are like really happy with that? Yeah, I was hoping you might say, I'm not happy with that. Can you imagine how far off you'd be in astronomy if you had, astronomy, you got to be, all right, April Fools, all right. Yeah, I mean, hey, we had a pretty big step size, h equals 0.1. So it's kind of surprising that the tenths decimal place is in agreement. But we'd like to have, Thomas, I want to make you happier than you are now. How can we get a better approximation than what we had here? That's right, Zachary and Antonio. Decrease your step size. Decrease your step size. Okay, decrease your step size. Okay, so I want to make sure I'm gonna go to the MATLAB program, but I want to make sure everybody's copied it down up to here. Copied the solution down. Well, Gisha, it is possible to, well, Antonio, when you say infinitely small, what Antonio means, I think, is just take smaller and smaller and smaller step sizes, and it's going to get, the approximation will get better and better and better. And with the computing power that we have these days, we're able to do that. We are able to do that in our classes. So let me show you, let me go back to the example that you copied. Are we good here? Is everybody copied okay? Okay, all right, very good, very good. All right, so going back to the example here, when we used the step size of h equals 0.1, we needed five iterations. So if we wanted, like in part B, to do a step size of 0.05 to approximate our solution at when x equals 1.5, how many iterations would we need? Well, it would have to be more. That's right, Ann. That's right, Antonio, double. So it would take 10 iterations. Because it's going to take more iterations because, you know, if you think about like the little graph, you know, think about the little graph, you know, you start off at 1 and, you know, you go out to 1.05. So you're going by 500ths. It's going to take, you know, more iterations to reach 1.5. Step size is half as small. So clearly, if we want to get approximations with this smallest step size, I mean, going out 10 steps. I mean, like for instance, in your homework, going out, you know, 2 or 3 steps, working out by hand is fine. I may on the next exam specify that you go out the first do the first 2 or 3 steps of Euler's method by hand. But then any steps beyond that, you know, that would demonstrate that to me that you know how Euler's method works. But then steps beyond that, we could use a MATLAB program. So let's go to the MATLAB program here. And again, we'll go to the MATLAB program to justify when we had a step size of 1/10 to justify these 2 iterations here. All right, so let me unshare here on that. Let me go into the Blackboard. So everybody should go into the Blackboard. And one moment here, let me go in as well. Okay, one moment. Share application. Okay, so can everybody see Blackboard all right?
Yes.
Okay, good, good. So what you do is you go to MATLAB Programs, Helpful MATLAB Programs, click here, and here's a new one, Section 2.6, Numerical Method. There's an Euler's Method program. Just click on the link here for MATLAB program. It will help you approximate values using Euler's Method. Click on the link, and it'll bring it up. It'll download it on, like, you know, you'll see it being downloaded. And then you click on that M file, that MATLAB file, and it should bring it up. Should bring up MATLAB with the file in the editor. Okay, so on that note, I'll have to go into the MATLAB here. So just one moment, class. So mine's still coming up, my MATLAB. One moment now. Okay, so let's go, let's see your application. Here we go. Okay, how many are seeing this program right here?
Yep.
Okay, good, good. So this is this program, as it's written, is to compute the approximate solution of the differential equation y prime equals 0.2 times x times y, where we have h equals 0.1. Yeah, okay, so let me show you a few details here on this program. Okay, so first of all, the way this, I have something here called clear variables. What clear variables does is when you run the program, it clears out any variables that are in the workspace, because if you store variables and somehow they accidentally get used in a program, you don't want that. So that's what clear variables is for. And then our initial condition is x1 equals 1 and y1 equals 1. Now, I want to be careful here. Our initial condition is x sub 0 equals 1 and y sub 0 equals 1. But the way this program is, the counter starts at 1. Okay, so this is just how you specify your initial condition. And then your f of xy, okay, is equal to 0.2 times x times y. So we start off initially with f of 1. It's not, I want to be careful here. That 1 on the left means it's your first iteration. Okay, that's what it means. Okay, and then h equals 0.1, and then you have a for loop. How many have seen for loops maybe in other programming classes? A for loop or a do loop, something like that, or a while loop. Has anybody seen that in computer programming? Okay, so this is just, thank you, Ann, thank you, Thomas. This is just a simple for loop. And I goes from 2 to 6. How many is that? Iterations is that? 2 to 6. Right. Well, here's the thing. It's going to be 5. It's 5 iterations, because it's like when I equals 2, that's the first iteration. When I equals 3, that's the second iteration. It counts from 2 right to 6. So everything here is coded. And what you can do, and of course, for your problems, like you'll have a problem with a table where you have to do, well, if you have a problem with a small step size, you use this program. What you have to do is you have to change certain lines on the program. So you might have to change you might have to change, for instance, this here. You might have to change this here. Well, and you might have to change this here. Well, you would with a different differential equation. And then naturally you'd have to change this here. Okay. And then depending on your iteration. So, it's sort of like you just try it out and you'll get the feel for the program. Okay. Sometimes you just have to study the program a little bit, and it'll make sense. So let me see here. Hold on. I don't know why let me bring the program back here. Where is my program here? Hold on, class. One moment here. I don't know why my program went away. I don't want my program to go away. So I'm opening up my program again in MATLAB. Okay, and sharing, going to here. Here we go. Okay, so what I'm going to do here is want to bring this up. So I'm gonna select all, select the whole program. Okay, I'm going to copy it. I'm going to paste it on the command line, and then I'm going to hit enter, and it will give here the X values, and then there are the Y values. Now, one thing I want to do here, let me see. Maybe I'll do this right in the code. Can you all see the code in Blackboard there? Can you all see the code? Or are you just seeing a blank?
It's a black screen before we
Yeah, I don't
could.
know why it's doing that. I don't know why it's doing that.
Now we can see it though.
Now you can see it. All right.
Yeah, we can see the output too. Yeah.
Okay, let me try something here. One moment. Okay. Paste it, enter. Okay, good. So what I did is in the code, I added a command called format long. You see that there on line 15? I added a command called format long. And the reason I did that is so I can get enough decimal places. Because WebAssign, when like you're going to be completing a table and talking about percentage relative error and all that, to get the answers right, you have to go out enough decimals. I would say 8 decimal places after the decimal point. So use format long, and what I can do is I'll put the program back in the I'll add that and put that revision in the program. But just in the code, you can just put format long after the end statement. Format long gives you a lot of decimals, and you can see that the last value here, 1.125878843. That's the value we got. Okay, are there any questions on this? Okay, all right. All right, I'm going to do a little save here. I'm going to save that. All right, so now what if we wanted a step size of 0.05? Well, h equals 0.05. That's going to then increase the number of iterations to 10. So we're not going to go from 2 to 6 anymore. We're going to go from 2 to what? 2 to 11. That's right. Very good, Matthew. Okay, and so what I'm going to do is I'm going to CLC here in the command line to clear the command line. And then I will go in here, select all, copy, and paste it in the command line. That's how I like to do it. And now I get a value here of, let me just see if there are any questions. One moment, class. Let me just check one thing here. One moment, class. Hold on here. One moment. Let me see here. One moment, class. One moment. I'm not sure. Hold on. Hold on.
We have to change H to 0.05, right?
Oh, thank you, Matthew or Christopher. Well done. Well done. I didn't change that step size. Yeah. All right. Yeah, got to change that step size. You're right. Well done. Everything else is fine. All right, so let me CLC here. Clear the screen. Thank you, Christopher. All right, we'll copy. We'll paste here and hit enter. There we go. So here's the value, 1.1294668 rounded to 8 decimal places. And that is certainly closer to the exact value of 1.1331485. It's not like great, but it's certainly better. It's certainly closer. And you see, with this program, you could take a step size of, you know, 1,000th, and then, you know, of course, you have to, you know, figure out how many iterations. But there we go. Are there any questions on the program before I go back to the problem? We want to finish out the problem here. Okay, all right, then on that note, let's go back to the problem itself. Zachary, the 2 to 11 gives you 10 iterations. So 2 to 3, 3 to 4, 5 to 6, 7 to 8, yeah. You have to start it in the program the way since your initial condition is x parentheses 1 and y parentheses 1 equals, your first iteration would be then 2. So that's why you start at 2. It's different, like when you work it out by hand, you start at x sub 0 and then y, you know, and then y sub 0 and then y sub 1 is your first sub iteration. But with the MATLAB program, you start at y sub, I got to be a little careful. Well, y sub 1 and then y sub 2 is your first iteration. It's just because you know how MATLAB counts things. Good question. Good question. All right. So now, with the step size of 0.05, 5/100ths, we get a better approximation. And we use the MATLAB program with 11 steps. It's still not great. But it's closer. So then we get to part C. We talk about something called the percentage relative error. So the percentage relative error is basically, you want an idea, percentage-wise, of how far off well, I want to be a little bit careful. I want to say this the right way. Hold on. It's called really, percentage relative error. It's how far off you are relative to the answer. So to do that, what you do is you take the difference between your actual value and your approximation, okay, the actual value minus the approximation, that's your error in your approximation, and then you divide it by the true value, okay, and then you're going to get 0.0064, but then you multiply that, well, you convert that to a percentage, okay, you convert that to a percentage, and that's going to get you your percentage relative error. And let me just check one thing on this while I'm at it. Let me just check one thing. I want to be a little careful here. Hold on, class. Hold on. I think I have something a little bit wrong here. Hold on. Yeah, this here, actually there's something that's not quite right here. Hold on. I don't want this. This is the percent right here, because I multiplied by 100, right? So this is the percent. Okay. That's your percent relative error. Okay, and let me just see before I move on here. Let me just see. One moment, class. One moment. Let me just check one thing here. One moment here. We do. Well, when I multiply by 100, I do get 0.0064. And what I'm doing is I'm looking at, yeah, no, actually, hold on. No, I'm wrong. I'm wrong on that. I'm wrong on that. No, this is the actual percentage. This is the percentage relative error right here. No, I'm correct on that. That's correct. Okay, that was correct. And it's just another way to measure to measure your error. You see, if you take the difference between the actual value and the approximation, you determine an error. But relatively speaking, how bad is the error? That then is the percentage relative error that tells you that information. Okay, may I go to the next page? We're almost done here. Are there any questions? Okay. Well, so I'll tell you what. Can you try to compute the percentage relative error for the step size h equals 0.05? Can you try to do that before I go to the next page? And let's see what you get. Okay. Let's see what you get. Okay. Let's take a look here. So, let's see. Zachary got 0.325%, and Christopher saying, wouldn't it just be half? And that's right. That's right. That's right. Very good. So, yeah. Using h equals 0.05, the percentage relative error is found to be 0.32%. And note, when the step size was halved, from h equals 0.1 to h equals 0.05, the percentage relative, I should have error here, percentage relative error was halved as well. So take a moment to copy that down. Let's see here. Question. Michael, have because the order of the error is order of h. That is, I got to be a little bit careful because my understanding of order might be a little different than yours, but that's correct. That is essentially correct, Michael, what you're saying in the chat line there. Okay, so giving folks a moment here to copy it down. Are there any questions at all? Okay, Christopher's good. Yes, Paige, I can go back 2 slides. We're good here? All right, let me go back 2 slides. All right, Paige. Okay, Paige is good. All right, 1 moment here. Okay, you're welcome. All right, so are there any questions in general about what you've learned today with Euler's method? Who's feeling reasonably comfortable? Yeah, I agree. All right, well, let me stop the recording.